Hi, I'm Alex, and I would like to introduce a joint work with Florencia Leonardi and Magno Taironi from University of São Paulo here in Brazil, called Model Selection Criteria for Regression Models with Splines and the Automatic Localization of Knots. We basically worked with spline regression models and the problem of determining the number and the positions of the internal knots that are required to perform this type of regression. In fact, the main idea of spline regression is to fit a polynomial on each segment of the function domain determined by these internal knots in such a way that these polynomials match at these knots smoothly through a continuity conditions imposed on their derivatives. And typically the result is a smooth curve fitting that is used to estimate a large variety of smooth functions. We studied mainly the question of determining the number and the positions of the internal knots automatically. In fact, it's a very important question because wrong specification of internal knots can lead to overfitting, underfitting problems, for example. So if we put an excessive number of knots on a determined region of the function domain, we can overfit the data on this region. So it's very important to have a good determination of the number and the position of knots. And there are some studies in the literature that provide an automatic method to determine these values, or just the number, or just the positions of the knots, but few studies concerns about a completely automatic method to determine both the number and the positions of the knots. So the goal of our study is to provide a not completely automatic method to determine these values. Okay. So we start with the classical non-parametric regression problem with an unknown function f to be estimated through the observation of endpoints contaminated with a zero mean randomized with an unknown variance sigma square. So this is typically the spline model. We extend this unknown function in spline basis through the determination of these knots, and then we have as a result, for example, an mth order spline regression model if we fit an mth order polynomial on each segment of the interval. In our problem, we set as parameters the coefficients of the spline basis expansion or some extension of splines, for example, B splines, natural splines. And we also set as parameters the number of internal knots. We set as K, we denote as K, and the K positions of these knots, T1, T2, Tk. So this is our parameter vector. And we propose the estimation of this vector through the minimization of a penalized least squares, where the penalty is the number of segments determined by these knots. So if we have K internal knots. Then we have k+1 segments on time domain. And we impose a penalty to control the smoothness of the estimates here on the adding the sum of squares. We have, as expected, a tuning parameter lambda that is typically determined by cross-validation methods, and theta is determined as the argument that minimizes this quantity. We perform this minimization process computationally, and we performed some simulation studies to evaluate the performance of the method using cubic B-splines as underlying functions with 1, 2, and 3 internal knots. So we have 3 underlying functions. We added zero mean, normal noise with variance determined according to 3 signal-to-noise ratio values, 3, 6, and 9. We also define 2 sample sizes, 100 and 1000. We input a minimum distance between knots as 15 to avoid knots determined too close with each other. And for each scenario of underlying function, signal-to-noise ratio, sample size, we performed 1000 runs. So we have here the table with the results for one scenario of sample size 1000 and signal-to-noise ratio 3. Then, for example, when we had an underlying function with 1 knot, 10%, 100% of the estimates of K estimates correctly the number of knots as 1. And here we have the mean, the median, and the standard deviation of the estimates of the position of the knots, very close to the true value, 50. And here we have a 95 confidence interval for this parameter. Here we have the curve estimates. When we have the 1 internal knot, 2 internal knots. Vertical lines are the true position in blue, mean and median estimates in pink and green. Here is the result, the estimates for 3 internal knots. We also applied our method on daily new infected cases of COVID-19 datasets around the world, for countries around the world, and for some Brazilian states and cities. All of our estimation and prediction are available and daily updated on our website at University of São Paulo. And this is important to estimate, for example, change points. So we can apply this method to determine change points of the curves, for example, of daily new infected cases. Here we have the example of Germany, when the method provided 4 internal knots estimates. And the knots are estimated on the main location where, for example, we have peak. That is very important to have an accurately estimate. Here is the result for USA dataset We used for Germany and USA cubic B-splines. And here we have the result for Brazil using linear B-splines, and the method provided three estimates for the internal knots. So as a conclusion, we proposed a method that provides a completely automatic way to determine the number and location of knots in spline regression and extensions, for example, B-splines, natural splines. Our method had great performance in the simulation studies and could be applied in change point detection problems as, for example, the daily number of infected of COVID-19. I would like to say that this is a work under development. Nowadays, we are studying theoretical properties and optimization programming of the method. And our partial results are available on an archive paper. So I invite you to read our paper, to visit our webpage, and all the suggestions, all the comments are very welcome. I would like to thank you, to thank the organizers, and I hope that this presentation was clear. Thank you very much.